This is the first lecture of two for chapter 4. In this chapter, we will be looking at isomers of alkanes, cycloalkanes, and alkenes. But just a reminder again, isomers are compounds with the same molecular formula, but there is something different in the structure of these two compounds, of the isomers. So in today's lecture, what we'll be covering is a 3D representation or 3D representations. We'll look at more than one of alkanes. And these are the dashed wedge representation and the Newman representation. And we'll also look at conformers and energies of conformers. So we'll define conformers and we'll apply different aspects to these different conformers. But before we start anyhow, you will definitely need your model set. So my suggestion at this point is to pause the video, go get your model set, and come back and see. Okay? First, I want you to build this molecule using the models. And so first find a carbon. It's typically black with 4 holes there. And then get 4 of the white sticks, which are bonds. And then key here is 4 different colors. What I have chosen here is blue, white, red, and green. So we need 4 different colors around my sp3 carbon. So you can pause again and build this molecule. Once you've built this molecule, what we'll try to do is, our goal here is to see if we can communicate the structure, the actual structure of this molecule on paper. As you can see, one way of communicating this actual structure on paper is to take a picture and show the 3-dimensional arrangement of the atoms around carbon. Of course, you know the 3-dimensional arrangement of the atoms around carbon is a tetrahedral. It's not flat, it's a tetrahedral. So let's look at how we will develop a way of communicating the structure of this molecule in 3 dimensions. First, you will notice here that based on how the molecule is arranged, that this blue, this carbon, and this red atom are in the same plane. So if you're looking at your computer screen, it's right in the plane of the computer screen. And the white is in the back of your computer screen, or in your computer. And the red is sticking out in front. So the key here is the blue, the black, and the green are in the same plane. In this case, the plane of the paper or the computer screen. And the white is in the back, and the red is in the front. Okay? So what we'll do here is develop a systematic way of communicating that concept. So what we'll do is we'll draw a line. And this line here represents the plane of the paper or the computer screen. We'll use what's called a wedge to represent something. And we'll use a dash to represent something. So as you can imagine now, you have to be very careful when you draw your molecules, because now we're using a wedge and a dash. A wedge represents a atom or a group that's in front of the plane. A dash represents a group or atom that's behind the plane or in the back. So note again that a wedge is representing a group in front, and a dashed line represents a group in the back. And the line that's solid, that's in the plane, represents groups that are in the plane of the paper. So that is why this representation is called a dashed wedge. So be careful when you're drawing these structures. Okay. Now we're getting to a little more complicated molecule. So again, pause the video and build on that molecule that you have by getting another carbon and another red, another green, and then another white, and connect these two atoms, these two carbons. So now we have a molecule that has two carbons, and groups around each carbon. Okay, so once you've built that, turn on your video again, and let's look at this one. So let's look here. So in this molecule, this green, this black, and this black carbon, and now this red carbon are in the plane of the paper. So here is the plane of the paper. Solid line. So you know where we're going with this. This is in front. And of course the white is in the back. And the green here is in front. And the white here is in the back. So again, we cannot take a picture of these molecules and the arrangement of the atoms each time we're communicating. So what we'll do is we'll use the dashed wedge representation. So let us see if we can represent this molecule here, that's on this picture of this molecule here, in the dashed wedge representation. So once again, this is in the plane of the paper, front, and back. So what we have here is, here we go, that's the plane of the paper here, and this is in front, this is in the back, this is in front of this, based on this carbon, and this is in the back, and this is in front. So the dashed wedge representation. We'll be using the dashed wedge representation a lot throughout this course. So try and get very familiar with this. You'll need your model so you can see it, because what we're trying to do here is to take a three-dimensional molecule and communicate that dimensions on paper, which is of course 2D. Let us look here at another aspect of this molecule. So the same molecule we had, but in this case, let's rotate around this bond. When you build your molecule, you can see that this bond here is flexible, and there can be rotation about this carbon-carbon bond. So take your model and rotate around this bond. What you'll see is that this red comes up to the top, and that's shown right here. And you'll see that this green that's in front now goes to the back, and this white that's in the back now comes to the front. So I'm keeping this carbon here stationary and rotating this group about it. So now we have here a slightly different atomic arrangement of this molecule. Because of the slightly different atomic arrangement, they are called isomers, and more specifically, they are called conformational isomers. So pay special attention to that word. They are called conformational isomers because they're two different molecules, and the difference is based on rotation around a carbon-carbon single bond. So let us see if we can draw what we just shown on the previous slide. So here is the conformation that we have here. That was the one to the left, and that's in the plane of the paper. And this group is in front and the back, in front and the back. Because these groups here, this group and this group, are opposite to each other, we call this the anti-conformer, anti being across from each other. When we do the rotation by 180 degrees, notice a complete rotation by 180 degrees, this group comes up to the top, and you can see it over here, and of course these groups are switched. This group here comes in front, and this group comes in the back. Because these groups here are now on the same plane and right across from each other, this conformer is called eclipsed. So again, there are two conformers, and we describe them by giving them names. One is called the anti-conformer, so pay special attention to these names. The other conformer is called the eclipsed conformer. So what we're going to do here is, let us develop another representation of three-dimensional molecule. And this one is called the Newman projection. What you'll discover in chemistry, we have different ways of doing things, and each time some students can find one way easier and another way a little more trickier to understand. So we have different ways of explaining things. So here's another way of explaining or communicating a three-dimensional arrangement of the atoms. This was developed by Newman, a chemist, and his description is to look down this carbon. So determine a front carbon and a back carbon. So you look down the front carbon. So this is a sideways view, but now we're saying look down this carbon here and just describe what you see. So what you see is a carbon in front and a carbon in the back, which of course is blocked. And you'll see these groups bonded to that carbon in front, and you'll see these groups bonded to that carbon in the back. Of course, they're blocked by each. So what you should see is what's on the next slide, and here it is. So what you see is a front carbon that has a red, green, and white. And then there's a back carbon that you can't see because it's blocked by this carbon. And then there is a red group in the back that you can't see because it's blocked by this group. And so on and so forth. So this projection is called the Newman projection. Let us see how we write this though on a piece of paper. So what's done is we have here the front carbon, and we have one line, three lines actually, to show the three different groups on that front carbon. The back carbon you can't see, so we have a circle to represent that there is a carbon in the back. Behind this front group is another group. So because we can't draw it behind, we put it right beside it. So get it as close as possible to this group. Same here. This group in the back you can't see, so you put it as close as possible to this group. And of course the same here, can't see it, so get it as close as possible to that group. You'll notice that this would be the eclipse conformer, because these two groups here are right behind each other. So that's the eclipsed conformer, and we're using the Newman projection to draw an eclipsed conformer. Okay. Let us perform here a simple experiment. So we'll take the eclipsed conformer and using the Newman projection again, and we will rotate this by 180 degrees to put that down here. Remember that the carbon-carbon bond are flexible, so its internal rotation is possible. So after you've done that rotation, this is what you get. This red will be down here, this green will be over here, and this white will be over here. Notice it's 180 degrees. So it's completely turning by 180 degrees. So you'll notice here that this conformer is no longer the eclipse, but it's the anti, because these two groups that are in the plane are opposing each other, are right across from each other, opposite sides of each other. So that's the anti-conformer, and using here the Newman projection to do that. Let's see if we can write that. So this is just another representation of this, where this is in front, and of course the front carbon, you see the groups now bonded, and this is in the back, and you still have the same groups shown in the same orientation. Okay, so let us see how we can write this representation on paper, or the Newman projection, or the Newman projection of the anti-conformer. So again, front carbon has three groups, 1, 2, and 3 in front. Three groups in front. So get your model and look at these three groups, turn the model facing you. You got three groups in front. The back carbon you can't see because this carbon blocks it. So you put a big circle here, and now you can see the three groups in the back. You can see this group at the bottom, and you can see this group at the side, and this group here at the side. So again, this is the anti-conformer using the Newman projection. So be able to write the anti-conformer and be able to write the eclipsed conformer using the Newman projection. So let us see what's on this slide. So one thing that you will have to be able to accomplish here is to utilize both representations, the dashed wedge representation and the Newman projection. So let's look at this. These two molecules here are the same, and the conformer are the same. It's an anti-conformer, or it's an anti-conformer, but two representations. One is the dashed wedge. Here's a dashed wedge, and the other one is the Newman. So what you need to do at this point is get your model and make here the anti-conformer and draw it using the dashed wedge, and turn it to the side and draw the Newman projection. Okay, so what you need to do is to look down this side here and get your Newman projection by describing the groups that you see. So once again, this becomes very involved here and lots of practice, because you will have to communicate this three-dimensional arrangement of atoms on paper. And the way we as chemists communicate these three-dimensional arrangement of atoms on paper is by using here the Newman projection or the dashed wedge representation. Okay, let's see. So here again is another example of the same molecule. This time it's the eclipse. So here is the eclipsed here, and this is the dashed wedge. So you can look at this atom here, carbon as the front, and here it is. And this carbon here at the back is at the back, so we use the circle here, and here are the groups that one will see if you look down this front carbon. So this here just requires practice, and you know what's from it. I'm going to give you a molecule like this, and I will say draw the Newman projection. Or give you a molecule like this, the Newman projection, and I'll say draw the dashed wedge representation. So be able to communicate back and forth. It's going to take time because you have to visualize that in 3 dimensions. This aspect in chemistry is very important, developing that 3-dimensional aspect of your thinking. So again, make sure you practice this, because we'll use this a lot throughout chemistry, and especially for the individuals who are going on to medical school and performing surgery. You'll see that most of the surgery these days are performed using robotics. So the surgeon actually looks at a 2-dimensional computer screen and manipulates the robot in 3D. So this skill or this aspect of your brain must be fully developed, and here's where it starts, or one aspect of starting that development. Okay, let's see what's here. So as a summary, so we have conformers. We have conformers here are isomers that are achieved by rotation about the carbon-carbon single bond. By rotation. So by rotation, this is the same. These are all conformers of this molecule that has the same molecular formula, but we're rotating about a carbon-carbon single bond. This is the anti-conformer, because as you can see, these groups are right across from each other, and this is the Newman projection of the anti-conformer. This is the eclipse. As you can see, these 2 groups here right across from each other, and these groups are behind and in front and behind, eclipsed. Here's a new one for you, the gauche conformer. The gauche conformer here is also described as a staggered conformer, because the front has a group here and the back, it's not directly behind. So this is called the gauche. By definition, the gauche is where 2 groups or large groups are right across from each other. That's the gauche conformer. We'll use those names in shortly. Okay, so let us see how we can apply this concept here. So let us look at the relative stabilities of conformational isomers. The stabilities of isomers. So let's first of all define stability. So if there are 2 bulky groups around a carbon, so here's a carbon, here's a carbon. This carbon has hydrogen, which is pretty small. It has hydrogen, which is pretty small, but it has bromine, which is pretty large. So look at your periodic table, you'll see that bromine is to the bottom right of the periodic table, which means it's large. So this carbon again has a small hydrogen, and a very large bromine atom. We'll define stability here as getting these 2 bulky groups as far apart from each other as possible. The furthest they can get is in the anti-conformer. Notice they're extremely, they're far apart from each other. So we'll define that as a more stable conformer. So now we're defining stability, or one definition of this stability in chemistry is groups being far apart from each other. Which means then that if we have the same molecule but we do the rotation around this carbon-carbon bond by 180 degrees, we'll get the bromine close to this bromine here. So now we have two large groups that are extremely close to each other. So now we're defining molecules that are not stable as having two groups close to each other. For some reason, we have defined in chemistry that if things get too close to each other, not stable. If they get far from each other, more stability. The example I usually like to give is when you get into an elevator, if there's someone else in the elevator already, you do not go and stand right next to that person. You kind of go to the other end of the elevator. And that's described as stable. Same here in chemistry. Two groups furthest apart from each other, stable. Two groups close to each other, not stable. I just noticed an error here. There should be an H. There should be an H for this H right here. So again, but the bottom line is that two groups that are close to each other here are not stable. So let us apply that aspect. So let us use here the energy profile. So we have here a plot, energy increasing in this direction. So low in energy is down in this area, stable. High in energy is in the top area, less stable. And of course here we'll do rotation about the carbon-carbon bond here. So let us put the different conformers on this plot here. So we'll start by the least stable. Notice the two bromines are behind each other, the eclipsed conformer. So that means that this is not stable, and that's why it is high in energy. If we should rotate this bromine, well, it's the back bromine here by 60 degrees, it's moving away from each other, so it's a little more stable. We call that the staggered. You'll see that to be the gauche conformer. If we rotate it further by another 60 degrees, it comes down here. That's the staggered. So they are now furthest from each other, and that's why it is low in energy and at the bottom of this energy profile diagram. If you should keep rotating this by another 60 degrees, it comes here, and now we have the eclipse. And if you take it and rotate another 60 degrees, we have another staggered, close to each other, but not directly behind each other. That's the gauche, and it's a little more stable than this because these two groups are directly behind each other, whereas here they're not. And of course, if you rotate another 60 degrees, you're back to this conformer. So again, this gives you an idea of the different energies of the different conformers by rotating about that carbon bond by 60 degrees each turn. So again, you need to recognize the different energy levels or the relative stabilities of these conformers based on the rotation or based on the location of these groups. Okay, let's turn our attention now to cyclic alkanes or cycloalkanes. Here, the smallest possible cycloalkane, as you can imagine, is cyclopropane. 3 carbons. As you can imagine, if you put 3 carbons in a ring, and I would suggest not building this using your model because you just may break some of those bonds because it's highly strained. But you can see that these bonds here cannot rotate. This carbon-carbon bond here cannot rotate. Likewise this, but mostly the carbon-carbon bond that has the groups on it, they cannot rotate. So because it's fixed, we do not have conformational isomers of cyclic structures, because you cannot rotate it 180 degrees or 360 degrees. They're fixed. So what we call this here is trans, because this group is on the opposite side of that ring compared to that group. Trans, across from the plane of this cyclopropane ring. This molecule has the same molecular formula, therefore it's an isomer, but it's different because this methyl group and this methyl group are on the same side of this three-membered ring. So therefore it's different, and it's an isomer, but we can get more specific and we call this a cis isomer. So the name of these molecules would be a trans-cis relationship, or cis-trans relationship. But again, convince yourself, these are different molecules, different isomers. I should say they're different isomers, same molecular formula, but different isomers. They're not conformational isomers because of restricted rotation, but now we call them cis-trans isomers. We can write them like this using lines, or we can write them like this using the dashed wedge. So notice this one here, the methyl group is the dash, and the methyl group on the other carbon is a wedge, meaning that it's a trans, opposite sides. For this one, this methyl group is using a dash. This methyl group is using the same dash to indicate the same side. So this is a cis. Of course, if the methyl group were described as wedge and wedge, that would be the same cis relationship as this one here. So, take-home lesson from this is that now you have to do a lot of thinking because there are lots of variations in these isomers. And now the challenge becomes, how do we communicate those variations on two-dimensional paper? Let us look at a larger molecule here, cyclobutane. As you can see here, again, restricted rotation. So if you build that molecule, it's a little easier to build, but still difficult to build because the bond angles here would like to be 90 degrees, but the real sp3 carbons would prefer to be 109.5 degrees. So it's a bit strained, very reactive, but to accommodate for the straining, we call this puckered. So it's a bit puckered ring here. So that's what it looks like. But if you put groups on it, such as the methyl group and the methyl group here, you can still describe them as trans and cis. So here's a trans because this methyl group is on one side of the ring. This is on the opposite side of the ring. So that's a trans. This one is a little more trickier to see because this methyl group here is on this side and this is on this side. And that's a cis relationship. That's on the same side, even though it becomes a little more, it's not as obvious. This one is much more obvious because it's on opposite sides, but because of the nature of the ring, it's a little difficult to see, but this is the cis relationship, and that's a trans. So once again, these are isomers, same molecular formula, but differ because of the arrangement of the groups in space. Opposite side, trans, same side, cis. Gets even a little more complex when we look at the cyclopentane. This one you probably can build using your model set. So build it and you'll see that now we have a little minor degree of internal flexibility. but it's not full. So these bonds here can rotate, but only within a few degrees. To accommodate for the strain, it's a little more puckered than the cyclobutane. And if you look at it closely, you'll see that you can describe the hydrogens as axial, HA, or equatorial, HE. Remember that the equatorial is on the same plane around the planet, and the axial is sticking up and below a plane. So what we have here is the equatorial here, HE. They seem to be all sticking in the same plane of this ring. So let's examine a couple. Here's one, here's another one, same plane. Here's one, and here's another one, same plane. So that's HE, or equatorial. But for each carbon, which has two more groups bonded to it, here's an axial. You can see this is obviously an axial because it's sticking above the plane. Here's another axial. It's sticking below the plane. So those that are sticking above and below the plane are described as axial, HA. Let's see the effect of putting some groups on this molecule, or substituting HA with a group, and another HA here, or HE here with a group. So let's look at this. So now we have two groups bonded. Here's a methyl group, and here is another methyl group. You will see that these two methyl groups are in the axial position because they're above and below the plane. Okay, so we have that as the trans 1,2-dimethyl cyclopentane. It's also known as, key here, another name for this is the AA, because they're in the axial positions here. So we call this the AA 1,2-dimethyl cyclopentane. Notice again the difference in names for the same concept. So let's look at the other one. So of course this would be the cis, because we have changed one around. So once you've changed one, you get the other isomer. So this would be the cis. And notice here, it's the equatorial axial 1,2-dimethyl cyclopentane. And that would be the cis isomer. So you have lots of work to do on this first part of the chapter. Build your molecule in 3D, examine it carefully, and the goal here is to communicate different concepts onto two-dimensional paper. We have different ways of representing this. First, we describe the dashed wedge representation. Next, we describe the Newman projection. And here for the cycloalkanes, we are describing in terms of cis and trans. Notice they're not conformational isomer. Cis and trans. And the larger the ring gets, where there is a little more flexibility in the rotation, here we have the axial and the equatorial positions, and we can describe these molecules or the relationships of groups on it as the cis and trans. So this is the end of this first lecture for chapter 4. So please take your time, go ahead, read along in the text, make sure you have your model set when you read, and so make sure you have this concept so you can communicate this. So continue to study hard, and I'll post the next lecture, which is the last one, on chapter 4 shortly. Okay? Bye.